Okay, so I guess we should start. Welcome to the very first workshop of MyoChallenge 2024. We appreciate everybody's participation in this year's MyoChallenge. So today's workshop will be mainly separated into three parts. The first part, we'll be hearing a little bit from the leads of two tracks, Eric and Xinhuan, to give an overview of what are the new variations introduced in the phase two, which is when the AI leaderboard has been open. We introduced a little bit of new variations in contrast to the testing phase we released before. So they will talk about what are those new changes and what you should take note of. They'll also be talking a little bit about how you will be ranked on Evil AI and how the matrix are calculated. So if you have any question in regards to this, feel free to ask your question in this stage, interrupt them at any time. For the second part of the workshop, we'll be going over how to submit your solutions onto Evil AI. This includes how to register a team, how to set up your token, how to do it via GitHub Actions or DIY. So hopefully after this, you will feel comfortable submitting your own solutions to Evil AI to rank them on other people. So the third section will be on an open floor to everybody to ask general questions to the organizers, including any issues encountered, any bugs encountered, or just a challenge in general, etc. So the floor will be open to everybody during this stage. So great. I guess we can start with Eric by introducing the phase two manipulation stage and including some demos. Thank you, Eric.
So I will just begin, if anyone can hear me, just to double check. So I'll just begin by showing some of the demos of the manipulation track. I believe this will be the host disable. Sorry, I need the access for sharing. If
Yeah, totally.
the overall idea is that we want to simulate the interaction between the real hand and the prosthetic hand. But just to be clear, with one of the disclaimer is that what we are trying to do in this task will be an upper bound for what happened in the real life because it's more challenging when the environment was not fully observed by the prosthetic hand in some cases. So I will start by sharing the screen of so so I'll start by sharing a demo. So we made a little change to the regular code snip with snipping the tutorial page. And by running this demo, so this will just show you a brief idea of what is going on. We are trying to manipulate one object from a start position to a goal position jointly using a hand that is simulated by a muscle skeletal model and a prosthetic hand. But in this process, to make it more challenging and more general, we involve some randomization in this process, including the position of the start and goal, also with the size, the weight, and the frictions to do with the object in the track. So we encourage our participants to come up with a solution that is more general and can be applied to different cases. For example, the boxes will be large in X, Y, Z, three dimensions so that it will have a more comprehensive behavior when really applied to, for example, a real test or a real scenario. Regarding the second stage, I want to emphasize on the evaluation matrix we used. This can be found also in our documentation page with a reference to how those numbers might change, but please pay attention that in the real scenario, the numbers might be slightly different. What we are trying to do is trying to test the environment that is more likely to be a real case, and we encourage the participant to come up with a solution that is as general as possible. So there are the primary success criteria will always be the success rate. So we will run your model for multiple times, let's say 100, for example, and we will count every time when the object was left on the goal position divided by the total attempts. If there is a tie in the success rate, we will move on to the second evaluation matrix, which is the time to complete the tasks. So, and please note that the failed attempt will be punished for full episode time which is also what really happened in the real cases. We want as much of successful manipulation as possible. In the case of the second time, which we expect rarely happens, we will also evaluate the muscle activations. This is the terms regarding the more psychological aspect of this challenge, and we want our models to use less the metabolic consumptions as possible. The details, including how the task will be evaluated and how the success is calculated, are all on the doc page. And if you encounter any questions or any bugs in this process, please feel free to raise an issue in GitHub or post it on the discussion channel so that we are able to help. We have opened the experiment or the challenge right now in the stage 1, trying to give you a sense of what exactly the challenge will be like for the second evaluation stage. And for the Evo AI, all the criteria are fixed right now, and those will be used in this process to evaluate the final challenge. And I believe that's most of the overview I'm trying to give right here. If you have any, for example, questions or something you would like me to clarify, please feel free to ask.
Okay, I guess thank you, Eric. If you don't have questions right now, it's okay. We can still we have like an entire 25 minutes later on open up for everybody for more questions. So I guess we can hand it over to Qinghuang to introduce the locomotion phase.
Right. So let me bring up the documentation. All right, can everyone see my screen? All right, great. Okay, so the locomotion track involves like a prosthetic leg and a good leg. So you're supposed to have the model walk over different terrains. So for well, actually to target people who are trying to get sort of who are new to machine learning. So we actually provide this stretch of flat ground. So the entire track is 100 meters. The initial 20-meter of the track is flat for people who are unfamiliar with RL to work on. And we also try to introduce this physiological metric track for it. Okay. So what we have is like we have different obstacles for you, and so these obstacles are increasing in difficulty as you go along in the track. So what you can see here is an example of what we mean by increasing difficulty. So for example, if you have the terrain as stairs, we progressively increase stairs height. So you get a patch of stairs going up and down, a straight patch, and another step. Is it visible for you? Okay. And okay, so for this environment, what we want is like we want to make it as realistic as possible. So that would actually mean that you have no way to interact directly with the prosthetic legs, meaning you cannot control the torque actuators directly. So instead, what it does is like the OSL, the prosthetic leg, actually implements a state-based impedance controller, where we actually provide you the API to update the controller parameters. And so therefore, what you are only giving to the environment is simply just the muscle control values, which is coming here in the action space. And okay, so we do also understand that some people might be also working with muscle models that are not RL based, and therefore are more used to having a control range of muscles between 0 and 1. So in this case, we also have this option during the evaluation where you can set this normalized act to false, So you don't get into this normalization between -1 and 1 for muscle control values. Okay, so this is the full observation space you are provided. During evaluation, you can actually pick and choose what are the observations you want. You can use everything. You can do calculated observations, but this is the only observation set you are given. Okay. Maybe I'll just go in a bit more into the terrains. So we actually have, oh, okay, sorry, this is probably is a bit more update. So we are randomizing with all the terrain types. We have a combination of flat, hilly terrain, rough terrain, and stairs. So hilly terrain essentially just means it's a small hill where you have to traverse over. And we do have a final kind of terrain code, which is called a mixed terrain. So essentially, we are mixing both the hilly, rough, and stairs, all three together. Okay. So the other thing is like the socket forces. So because of the way that the prosthetic leg is built, that you don't have direct control, the only way you can interact with the prosthetic leg is through the socket forces. So it's given as a 3DOF force vector, and you do have yeah. So one thing to take note is like the vertical force vector is negative, because it's projecting from the prosthetic leg into the residual limb. So finally, additionally, we also included a height map. If you can think of it as kind of a vision around your model. So because we do think that most likely you will need that, because you will need to see what kind of terrain you are walking on, like in front of you. Okay. Then there's also finally the state machine. I guess I'll just briefly go through it. I mean, interested people are kind of advised to look through the code if you want to. So essentially, it's a four-state state machine, just capturing the states of early stance, late stance, early swing, and late swing. So each state will contain impedance control parameters for both the knee and ankle actuators, which are given here in all three, like the stiffness, damping, and target angle. And so there are also state transition thresholds where you can determine that for example, if a load goes above a certain limit, you want to change the state. Similarly, we have that for the knee angle, knee velocity, ankle angle, and ankle velocity. Okay. So yeah, we do also include like documentation for the how you use the functions as well. Over here, like you can just simply go in and read them, which is yeah. All right, so for testing, during the phase one, we actually release we release two environments for you, like so MyoChallenge OSL run random and run fix. So for run fix, it essentially means that we are fixing it to just using the flat ground. So essentially you have a very straight track. I think in this case this would be just 100 meters for the model to run. For the random terrain, it will be you randomize the terrain, but we are not mixing the terrain. Okay, so essentially that's just a parameterization of the environment. Okay, so the success condition would be based on the average distance travel over 100 episodes during evaluation. Then we do have imposed an additional condition that the model would have to walk for at least 20 meters to be considered for ranking. Okay. Then if there is a tie in the first condition, which is the distance travel, we would have the second condition, which is the average time to complete the run. So do note that if the model falls, then this average time will be set to the maximum, which is currently 5 minutes, so 300 seconds. And so it's a pretty heavy penalty for falling. But if over 100 episodes, it should average out if the model is not falling. Okay, then there are two more additional physiological parameters, metrics that we are also looking into. So which is the pain measure, which is represented by the average amount of overextension torque on each rotational joint in the myo leg. Okay, then finally, we also have the total muscle activation as an estimate of the metabolic task. So if you could actually minimize that, then you will also be considered for the physiological metric. And I think, yeah, that should be all for the locomotion.
Do we have any questions in regards to the phase 2 variations for locomotion? Okay. Great. Then I guess we can move on to our second section of the workshop, which I will be giving an overview of how, after you have trained your policy, how do you submit it on Evil AI to compete it with other people. So let me share my screen. Okay, great. So can people see it? Okay, great. So this tutorial will be mainly on how to set up your entry to Evil AI 2024, and how do you, after you've trained your policy, how do you submit it onto it so you can compete with other people. So let me actually send this link into the chat so people can follow along. Although I only tested on locally, but this serves as a reference for everybody. So great. So the first thing that you want to do is actually to install Eva AI. So this ensures that either on Google Colab or on your local machine, you're able to connect with Evil AI through a command. After you have installed Evil AI, you will need to go to the web page and register your account. So I believe everybody here should already be registering your account since you wanted to participate. If you haven't yet, please, after this meeting, go register your account and start creating a team in your Evil AI MyoChallenge 2024. So how you will do it is you find MyoChallenge 2024, click participate, give an awesome team name, and create and click submit. After you have created your own team, what you will want to do is to find your authentication token. So this authentication token helps you link to your GitHub repository, helps it link to your local machine, Colab, etc. So how you obtain it is you go to your profile page by clicking on your name on the right, go to the authentication token here, and copy this hidden line over here. So if you have participated in MyoChallenge previously, please remember to refresh it because this due expires on a yearly basis and we have problems before if you use your own token. So after you have copied your own token, what you want to do is you want to use this command, which is Evil AI set token, to set up your token either on your local machine or on your Google Colab. And afterwards, you should run Evil AI Challenge Participant. If you have registered successfully both on Evil AI and if you have installed your local Evil AI successfully, you should be able to see the challenge that you participated in. So for here, I have registered for two different challenges, MyoChallenge 2023 and 2024. You should see MyoChallenge 2024 when you run this command. So after you have made sure everything is set up and you have registered successfully, something that you want to do is you want to clone our GitHub repository template. So you can submit it via GitHub Actions or via Docker. So what you want to do here is click on the repository link. You will be clicking on Use this template, create a new repository, which gives an exact copy of the template that we have onto your own repository. So one thing that you will need to make sure is to make it private. This is because you want to make sure that other people are not stalking your solutions and just taking over what you have as their own to make their submissions. So one thing that you also need to do is to set up your Evil AI token onto the GitHub repository that you have just cloned it using the template. So how you want to do is to go to the setting tabs of the GitHub, go and find the secrets and variable and click action here, and then click the new repository secret. Then paste the Evil AI token that you just copied onto this page at secret. This allows you to directly push via GitHub Actions later without any further authentication to Evil AI. So afterwards, you have successfully linked your GitHub repository to Evil AI. The next step will be to set up your personal access token on GitHub. This step should be pretty familiar with everybody who has been using GitHub regularly, but I'll still give a general overview. So basically, this PAT allows you to access your allows you to push or clone on your local machine or on your Google Colab or on a cluster without since like right now GitHub has a new authentication method. This allows you to do that. So how you will do it is to go to settings, developer settings, personal token access token, generate a new token. Please note that this token will only appear the first time that you see it. So you have to copy it and store it somewhere safe because you won't be able to go back and see it later on. So after you have created your PAT, you can actually now use your own PAT to set up your Git repository that you have just cloned it onto your local machine or onto GitHub Colab. So how you do it is you git clone your own repository, you're using your own PAT, blah, 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 over here. And something that you would like to do after you have successfully cloned your repository is to test it out. So you have to run this source setup no docker command if you're on a Google Colab, or you can directly run the setup docker command on your local machine. So what this command do is that it generates a small test with a random agent. So if this test compiles successfully, it means that your GitHub is set up locally or on GitHub successfully, and you can make your submissions seamlessly later on. So for Windows users, please note that you will have to install WSL to make it work. So yeah, if you use Windows PowerShell directly, there will be some syntax issues. So remember to switch to WSL if you want to try it on Windows. So now, how to train a policy section. I will not be talking about this because we have already created 2 tutorials on this. The first is how to train with random actions and how to visualize it, and the second one is how to get started with the baseline. We encourage you to take a look at those tutorial sections if you're not familiarized with how you can train your policy. So let's skip directly to the point that you have already a policy that you are happy with and you would like to submit it on to Evil AI to see how you perform among other competitors in this challenge. So what you will need to do is to modify your agent file to customize your observation and load your policy respectively. So for example, if I want to submit it to a manipulation track, what I would like to do is to navigate to the agent folder and find the agent manipulation npl random.py file. So for example, if we navigate here, we'll be seeing this file that you need to modify. The first thing that you will need to do is to change your custom observation key. So this is the key that you can change according to your training observation. So please note that the observation key that you can customize here must exist within the observation dictionary in the environment. You cannot define any keys outside of the observation dictionary. You can totally take out any of these observation key here and use your policy that's trained on a smaller observation set if that fits your need. So after you have changed your observation key based on your own need, you will actually have to load your own policy. how I like to do it is change this policy equals policy RC here to load your policy that you have just trained in. And after you have loaded the policy, you will need to modify your action control here. So it reads from the policy that you have inputted from an observation and output actions accordingly. So these are the three main things that you have to change onto this agent file in order to make your submission successful. Another thing that you have to note is you will have to change this requirement file to include all the necessary packages that you will need to compile. For example, if I train on stable baseline 3, you will need to import stable baseline 3 and its version here in order for the Docker compile to be successful. I guess like you also have to import stable baseline 3 here. So if you are using any other packages, do the same to make sure that your Docker file includes everything that you need. So after we have done all of these parts, for here we include another code modification which you can use to load your policy. And I guess we can take a look at the how Lattice, which is one of the previous winners, load their policies. So Lattice is the winner of the manipulation team last year. So how they change it here is they define a class agent method, which takes in an environment and a model, and they call it actively here from pi equals agent model and environments, and they then call their actions here through pi.getAction and input an observation state. So I guess this is totally public, so you can use this link as a reference to your own submissions if you have issues to create to load your own policy and write your own code. So yep. Let's see, so after you have modified your environment, you have modified your agent file, modified your dependencies, now you're ready to test your own agent. So how you would do it is you will run this test locally, test manipulation agent random.sh. So this will actually manually run a local evaluation on your computer. If this compiles successfully, you will be able to compile successfully on Evil AI. So after you have run this code successfully, what you want to do is to push your modified code to your repository. How you would do this is pretty simple. After you have pushed everything onto your GitHub, what you can do is you can trigger the GitHub submission action. So for example, if I navigate to my own repository right here and I have pushed it everything that I wanted, including my baseline file and modifications to the agent file, what I want to do is I want to go to this action tab right here. First, run a Docker build test here, run workflow. After this has compiled successfully, you would like to go to your phase 2 submission and then run another workflow. So this second workflow will trigger the submission and you can view it on Evil AI once this is successful. The entire process will take about 15 minutes for the actions to complete successfully. Great. So another method that you can submit is via Docker, if people prefer that. So on Windows, what you want to do is you want to download Docker Desktop. You want to clear all previous Docker image, container history, and cliche to make sure that you're compiling the latest version. And then you will be trying to build the Docker using this command. And afterwards, you can directly push the Docker to Evil AI following various commands that's listed under Evil AI. So you navigate to MyoChallenge 2024, submit submission actions, Docker-based challenge. You can actually see a list of Evil AI push commands that is for different phases, including manipulations and locomotion. You can also choose whether your actions can be private or public. So you can submit it on private first, and if you're satisfied with your score and how you ranked it, you can then make it public so everybody can see your submissions. So if you have pushed successfully via Docker image, you will see a output here saying that your Docker file is successfully submitted, and you can reference this number on your Evil AI system. So this tells you that your submission is successful, and if you go on Evil AI, you'll see that your submission is received, and you will be queued and run for evaluation and then ranked it among the other people. So we're near the end, and I would just like to stress that we do have Google Compute credits for everybody who wants to participate in the challenge. So if you are running your experiments on Colab or clusters, feel free to reach out to the MyoChallenge team to include your name, your team name, and your institute for a $100 credit, I believe. So is it, Chifa?
Yeah, I can chime in around here. So yeah, it's $100 credit per coupon. What you need to do is like simply just give me your name, your team name, and your institute.
Yes.
Then
So
yeah, I will just give you the code and you can just run it on your Google Colab.
exactly. So we do want to make sure that you're running it for the MyoChallenge, but not for your personal needs. So we do want your registration information and so on. So I guess this completes the tutorial right here. I hope it is not too overwhelming. I know it's a lot of information, but I have sent you the link to this Google Colab for you to try it out on your own, and all the information that you needed is right here. If you have any additional questions, feel free to open up a discussion thread on our discussion on GitHub, or submit an issue on GitHub if that fits your need more. So okay, great. So any questions on the EOLAI submission?
So Cheryl, if I understand correctly, so earlier on in the competition, I was under the impression, so there's this difference between the observations that the environment. I've been working with, I don't know if this is also true for the locomotion, but for the bimanual, you get observations from the environment, and they're different from the observation dictionary.
So yes, so I guess like the observation dictionary, you can actually customize and add a lot of information on your own. For example, in the default observation key, you will only have the agents, the MPL, the Mio hand, and the objects QPOS, like the position and velocity. However, in your observation dict, you can define something on a much detailed level. For example, you can define like how much, like where your fingertip is, how your angle joint is. So these informations, although you cannot pass it directly into your observation policy, you can use it to calculate your reward. So this is the difference, that even though those are different, the observation dig allows you to extract more information, which you can use to refine your policy later on, and then use it to train the actions. Does it make sense?
I think that makes sense. What I thought that you had said in when you were just talking then was that you can use, so when you were defining the observations, I thought you were saying you can use any observations in the observation dict, and I thought you meant for your policy as input to your policy.
So
Maybe.
I guess I can clarify a bit in here. So the observed dict is the full set of observation you will be receiving when you submit this, but you can take anything out of it and compute your own solution. I believe this better clarifies it. So for the fingertip position, for example, will be part of the hand or MPL joint positions, but it's actually extracted from the observed dictionary bound, if that clears what you're saying. But what I'm trying to say is that observation dictionary is the upper bound, so you can collect any subset from this, and you can also do your own computations to get whatever you want.
So you can use any of those observations in the observation dictionary as input to your policy.
Yes. So anything comes from the observation dictionary will be available to you at runtime or at evaluation time. You can take anything, do your own computations, and output as actions.
Okay, so I thought that maybe so at the moment, when you do when you reset the environment, or when you take a step in the environment, you get, so for the bimanual task, you get an observation vector that's 211 elements. I thought that was the observation that your policy had to take in at evaluation time, but you're saying that's not true. It can be more general.
So in theory, that was everything in the observation dictionary. So that will be the input to your policy at evaluation time.
I thought there's much more in the observation dictionary than 200.
Yes, exactly. But most of them comes from the computation itself. So that should be the
Oh, I
everything.
see. You're saying you can
Yeah.
do
You
your
can
own
cut, for
calculation.
example, the joint position is calculated by every joint, the joint angles is calculated out of the joint positions, if that makes sense.
Yes. Maybe I need to look into the code to have a look at how these things are calculated again.
Okay.
But that potentially makes sense.
So just one more thing. Sorry for Chen waiting. What I was trying to say is that everything come from the observation dictionary is available to you at evaluation time. What are not is that something directly extracted from the simulation environment will not be available. So there's a difference in the interface. For example, in the simulation engine, you can extract much more information directly under the current code setup. We didn't block that because it might help you understand the context of the task.
Okay.
But those listed or the default for the observation dictionary will be available to you. I hope that clarifies everything.
And just maybe one last question on this to fully clarify in my head. So the observations that Cheryl was just showing there, and she was
Yeah.
saying rid of some. Are they all of them? Because from that list, if I remember correctly, that Cheryl just showed, there's some others that I'm familiar with that weren't on that list. So was that a comprehensive list that Cheryl showed or not?
That's the comprehensive list. I think you're referring to something like the joint positions, the hand orientations. Those are the actually computed out of the default ones.
Okay.
So you can do your own calculation based on that, but that will be all that's
And
available.
things like fingertip positions as well, because I remember they came from what I remember, they
Yeah.
were things that came from like MyoChallenge that weren't
No, I
calculated
think
in
it's
that.
coming from the joint positions.
Okay. Okay. All right.
So the joint position will cover that part but we can double check and add it to, but everything on the observation dictionary you are free to use.
So to calculate the fingertip positions, where you have to do like all the forward kinematics, you'll need to know all the link lengths and you'll need to know all this extra stuff, won't you?
I think in the Majoko, because we define that position as a geom, you have the information at the time, and it will be available in the observation dictionary.
Okay. Okay, thanks.
But if you have further questions, feel free to post it on this discussion
Sure.
channel or GitHub, so we can look into that and give you a firm answer.
Sure. I'll try and do it myself, and then if I have any more questions, I'll let you know. Thanks.
Thank you.
Okay, I think so. Maybe James, let me share my screen so you could probably get a better idea what you're trying to say. Okay, are you able to see the code here?
Yeah.
Right. So this is in the manipulation environment. So if you look into this get obsdic, these are all the observations that are available to you. Okay. And in the evaluation environment, you would notice that there is something called a custom ops key. So by specifying the keys here, you can actually access them right over here. So by default, I think it gives everything. No, sorry, just to clarify, the environment itself has a default observation key. So if you are not modifying this key, it just simply takes this set of keys, which you can actually see that it's not the full comprehensive list. So the full comprehensive list comes from this get obsdic. And if you want everything, you just need to specify all the keys here in the evaluation environment. So this would build your Docker. And when you are, so that's, and we actually provide functions like this to extract all these custom keys that you want. So I mean, some like so you're also free to do calculated observations here. So for example, if you want maybe if we give something in quaternions, but you want them in Euler angles, you will need to like recalculate them. So in this case, that this function is the one that allows you to do that. Okay. So there's this thing about being able to modify your observations during evaluation. So this is actually what we meant. So you have this full list which you might not use everything,
Yeah,
and by defining them, you could actually you're actually customizing them in this way.
I see. All right.
Does that make full sense for you right now?
Yeah, I think that makes sense. Yeah. You're saying that the stuff that you're showing down below, if it's not in that custom ops key, I can just put it in that custom ops.
Yes, you can put it in this custom ops key, but with the caveat that it has to be something available in this entire list right here.
That makes sense. Thank you.
If you have something called like body position, so it will just give you an error because this is something completely not available in it.
Right, I see. That makes sense. Thank you very much.
Right. Okay. So maybe just to clarify a bit, the same format is also in the locomotion track. So we have all these observations here. These are the full set of observations, and in the environment, you can define what you want. Okay. Right.
All right, thank you, James, for the question. So now the floor is open to everyone for their personal questions. So feel free to bring up anything that you encounter during the training. Yeah. So if there's no question,
I have a couple more
yeah.
questions if nobody else has any questions. So one thing that I was just trying to so an observation that I was trying to calculate for myself purely for training purposes, so I know this wouldn't be available at evaluation time, was because I don't think it's part of the observations that we get, is the tips of the fingertips for the prosthetic hand. And I just wanted to know if somebody could give me some feedback if they're familiar with the XML files for the hand, for the prosthetic hand, whether the things that I think might be the fingertip positions are or are not. Is there anyone here who is familiar with the XML files, or is it something I can?
I guess I can answer that questions. So there's a bit trick you can do. So if it's actually defined, for example, the relative position of the gem file, you can locally create a larger sphere in this case in the same position just by adding it to the XM files. So I'll visualize it in that corresponding position. Okay, so let me try whether I can give you an example for this. But I have been working on something else, and this do work in this case. So if you look at so I would just give you, sorry, I probably want to share my screen in this case. Yes, so if you look at I would so for the So for anything in this side, just give maybe okay. So the arm is something I'm more familiar with. So just give you example in the my arm. For example, if you want to know the fingertips position, you might want to. What I would try suggest is that you navigate to the fingers, and for the finger hand, it's really around here. So this is the some distal positions and all the positions. And when you think this body name will be more likely for the positions, you create a new gem with just colors with position 000, so it will spawn in the same positions. Then it will just give you a visualize of a sphere in the environment. So you got to see what is going on right here. And you can extract the position of that of that part by getting the genome ID or the body ID, depending on what you use. But this should be able to help you find all the positions in this case. So this, I believe, is a distal joint. I think it's the first of the finger. If you spawn one of the spheres genome, it will just give you a sphere on the fingers in the simulation environment.
So for the MyoSuite hand, I think they're one of
This
the
is for the MyoSuite hand. Then the same applies to the MPL hand. So you might need to like navigate through this because it's a quite a messy arm. I think the same happens over here, but I'm not sure exactly which part of the code will work. But you might like try like do a attempt by trial by arrows approach.
I see. You're saying that you're using the visualization to identify whether that body site is actually the thing you think it is. Is that the idea? And then
Yes. It will be a dumb solution, or otherwise you can maybe check the documentation in this case from the MPL side, but I'm little uncertain about that part because I'm not entirely familiar with that.
no, that's useful. That's a useful suggestion.
Yeah, maybe I can jump in. So actually the MPL, how MPL is defined is a little bit different from the MioArm, or like not different, but like how the germs are defined are not intuitive in the sense like a human arm. Like for example, MioArm, like palm is palm, thumb is thumb, everything is what you think it is. But for the MPL, I think how they coded it is not really one-to-one. So for example, if you reference the sum, it's actually not the sum. So when you reference the palm, you have to, it's actually like palm 1, palm 2, it's not like directly the palm. So like you will have, if you want to do the center, you have to take the average from the two. So I think especially for the MPL, you will have to actually visualize to make sure that you are calling the correct thing, because that happens to me during the baseline training, that like what I'm calling was not actually what I want. So yeah, so I think the MPL commands or like the naming condition is different from the Mio hand, and you have to do a little bit of digging to make sure that you're doing the right thing. But if you have more questions, please open the discussion on GitHub, because Valine, who is the main creator of the XML files, will be able to give you a more detailed answer on like which one you should be calling if you have very specific questions. For example, oh, if I want to call the palm, if I want to call the fingertip, but I can't get it to work, you can open up a question. I think Butling will be able to help you more and give you a specific answer on that.
Okay, great. Yeah, thank you. That's a really helpful suggestion.
Perfect.
Maybe also if it's not related to the challenge, right, and you want to use the model for your own purposes, you could actually make a little hack. This is just something fast. You can define your own sites on the fingertips if you want, and then read from that site directly. Because in Mojoko, sites are not are just I wouldn't say objects. They're just something tagged onto the model. It will not affect the physics, or it will not affect anything. But what the nice thing is that it will give you the position. So if you're interested in just the fingertip positions, which is like not available for the challenge, you can like define sites on every tip,
Right.
and you can still read them based on you just have to define them in the XML yourself.
Okay, great. Thank you. My last question was, so the sort of randomization of the environment in this evaluation phase. Are you guys familiar? So I know something like Stable Baselines 3, it has recurrent PPO, a recurrent version of PPO. So I'm thinking that if the environment's partially observable, you're not told some information about these features that are being randomized, having a recurrent policy might be useful in that scenario. I've been sort of developing some framework that for other reasons is more of an off policy method. So it doesn't really work with something like PPO, which is on policy. And so I was wondering if you guys are familiar with any kind of stable baselines-y kind of things where they have like recurrent off-policy methods or recurrent SAC, because I feel like developing my own like recurrent version of SAC is a bit of a mission in itself, like without even dealing with the MyoSuite stuff.
I think they have it in the contributions. It's like stable baseline 3 contrib. It is a different repository altogether, and I think they have the recurrent version. Okay, if I'm not wrong, it's just the recurrent version of PPO, not the SEC. I haven't been following it for I think quite some time. So, but I do know they have the recurrent version of PPO.
Yeah, they have it. It's just, I guess it's yeah, if nothing else, it's feedback that that's
So
that's limiting to some extent, or it's an extra hurdle, I guess I should say,
Yeah.
to engagement with the task, with that particular feature of the task.
So regarding your questions, I don't think at this moment they have a recurrent SAC from stable baseline. And to the best of my knowledge, I don't think there's works being done in this aspect. So you might want to like use this as one of the publications. I guess it's not for us to comment on how you want to do it, but that sounds like a very good idea. So upon the visualization and the change, so what we applied are very gentle in the testing environment, and I don't think there will be a very huge change in terms of mass, shape, etc. So, for example, the muscle forces will mostly be enough, even the maximum weight has been added, and it will be pretty robust using RL to these purposes.
Okay.
So I hope that clarifies. But yeah, I think that will be very interesting and will be a very strong publication or a strong algorithm that you're developing. For example, last year the guys are developing the lattice algorithm and they actually won the challenge. But I guess it's not for us to comment on this kind of things right now. Yeah, but if there is anything to do with the challenge, we probably can answer that part of the question.
Okay. Thank you.
Yes.
That's all the questions I have. Thank you very much.
Yeah, I think part of this challenge is to encourage both solutions from the ML side and solutions from the physiological side, and like how they combine. So I think for Lattice last year, they are developing like a Lattice algorithm by themselves, and they see this applications on MyoSuite, and MyoSuite is actually like a very good demonstration of how this works and how this applies to like physiological biomimetric behaviors. So I think like if that's something that you are already on your track, this could be totally like one of the things that you can work on and make like publications on like NeurIPS, or like just show in our workshops and like participate in our benchmarking paper in the next year if you wing it. But I think it's like very interesting what you're talking about, including recurrent as part of the algorithm.
Thank you.
So we are reaching the end, so maybe Hawking can do some advertisement on the round table that's coming up.
Yeah, we have another roundtable on Wednesday. We invite the last winners from the past year. I think the designer of the lattice, right? Alberto is the designer of the lattice, yeah, to give a talk. Like, yeah. Yeah, we are going to publish the information on the Slack pretty soon, I think. Yeah.
So yeah, if you want to talk to the winners about how they win the challenge, any questions for the winners, yeah, please sign up for the roundtable that's coming up in 2 days. Okay, I think that's pretty much it. So thank you,
Guys.
everybody.
Can I quickly ask two questions?
Yeah, totally.
Yeah, so the first one is I think I don't have access to the collab notebook you shared. So
Oh, I don't? Okay, so sorry. Did I
Yeah.
not change the yeah, so sorry. People should have told me earlier.
yeah, okay. So my second question is pretty simple. I want to make sure if I can modify or customize the environment used in the, for example, in the bimanual task, there are some certain environments given from official but I want to, for example, only for the training purposes, I want to create another environment from that and train, for example, only with MyoHand. I want to train only MyoHand in certain environments. So is it possible to train the model in different environments?
I guess I can answer this question. So if you take a look at the init files in the same folder of the bymenus.py, you will see how the environments are created in this sense. It will be very complicated, of course, but I believe you can you just remove the part of the MPL hand with just a Maya hand alone. But what we have done is that we ensure that the single Maya hand will not be able to reach the goal position in this case. So if you completing the old task with a single Maya arm might not be a feasible solution in this case. But you can do whatever editing on the XML files, on the environments. It's all open sourced, so I guess there's no problem for you to do it. But for the evaluation, just to make it fair and accessible to everyone, we have to follow the same file in the evaluation challenge. But to train the policies, you can do whatever you want. This is purely open sourced.
Okay, thank you. I just wanted to make sure if it's allowed to do that.
Yeah, and also if you just want, if it's just for like playing around and knowing the environment purpose, knowing like the MioArm environment purpose, you can just directly call the MyoChallenge from last year, because we are using the exact same Mio hand as last year challenge. So if you just want to test out how Mio hand works on its own, you can call that environment. But this year we are evaluating on both hands, so your final policy will have to utilize both limbs basically.
Yeah, okay.
So maybe I can give a bit more heads up in this case. So if you can see how my Majoko is run. This is run by the Majoko simulate file. When you build the Majoko engine locally, you can just drag over the Maya hand. And sorry, I'm using a touching pad, so this is a bit weird. But what I'm saying is that you can also control all the muscles in this case, and it will change in the simulations just to get a better understanding. Sorry, I'm trying to zoom in, but I'm in a touchpad. So, what I'm trying to say is that this will just, for example, the arms are raised by manipulating the muscles. It will drop if slowly if this is not a contraction, but this is something you can play around in your own time. This is directly from the MyoSudo repo from the MyoSim. Just drag this XM file in a Majoko simulator and you will be able to do a bunch of things.
Yeah, thank you. Yeah, I actually already created some bunch of environments, so.
Okay, great.
Yeah.
Any final questions before we end? I guess then that concludes our workshop today. Thank you everybody for coming and thank you for all the questions. We hope that we clarify all of them. If there's anything else, please follow up on GitHub or our Slack session. We actually do have a MyoChallenge 2024 Slack channel. It's public. We just haven't advertised it, so you can totally join and ask questions there as well if you want. And thank you again. So I think Hawking can stop the recording, and thank you everybody for coming.